Third time's a charm, right?
Okay, now I can see your camera. I think we have some people on two different Zoom meetings.
Let's wait for it. It might be your, if you can turn your sound down all the way. Your sound down. Is that any better?
Yeah, it's way better.
So you can hear me now?
Oh, there's a bunch of like echo.
Feedback? How about now? Okay, but can you hear me with clarity? Because I had to turn the room sound down a lot. Excellent. Thank you so much. I'll turn it up a little bit more. Walk on the wild side. Okay, so. I can't hear you. Okay, text them in the chat box and tell them to rejoin you. Okay, so this is just review. And fortunately, this is recording. So those who are getting back online, let me just make sure it's recording. So this is all review from last time. Last time, what we went over were three fluid properties: density, specific volume, and specific weight. And before I was so rudely interrupted by the technology, in this class we will use water very commonly. And so a lot of these numbers you will commit to memory, but these properties are temperature dependent. That means as you change the temperature, the value changes. If a temperature is... Yeah.
I'm sorry to interrupt you, but we're getting a few chats, people saying they cannot hear you talking.
So, are there two different...
What if the PA is on?
Because some people said they heard me. Ms. Davis said she heard me. And so she can hear Christine's.
Also turn on my microphone. I guess they can.
So, if you don't see temperature given in a problem, again, just assume room temperature. Obviously, when you leave here and you go into consulting, you're going to have very specific applications. So if you're building something underground, typically you would use the average annual ambient air temperature because that's typically what you have below 5 or 6 feet. If you're building something up in Greenland, you're going to use a colder room temperature or outside temperature than here. So again, for the purposes of this course, if no temperature is given, you will use room temperature. If a temperature is given, you need to use the fluid property associated with that temperature. So room temperature values we typically use for water in BGS is 1.49 slug per foot cubed, and in SI 1,000 kilogram per meter cubed. And for and obviously specific volume is the inverse of that. For specific weight, for water, 62.4 pound per cubic foot, and SI 9,800 Newton per meter cubed. Again, these are all in the appendix to your book. So for homeworks, exams, labs, you have your book available to you, and you can also use the internet. Okay? So again, those are typical values. And then the next thing I wanted to get to today is specific gravity. And specific gravity is typically identified by the capital letter S, and it's defined as either the density of some substance, some liquid, gas or fluid, to the density of water. And the purest definition is the density of water at 4 degrees C. In a relativistic sense, sometimes more casually, people will just use the density of water at whatever the temperature they're looking at. So you know from the lecture last time, if we multiply both numerator and denominator by the acceleration due to gravity, this is also equal to the specific weight of any substance to the specific weight of water. Because you're basically multiplying the first fraction, density over density, by 1 in the terms of gravity over gravity. So specific gravity, since it has a variable in the numerator and denominator with the same dimensions, is a dimensionless variable. As I've mentioned in here in the first class, whenever you write a number for me, unless it's dimensionless, you need to have the units after it, always. It's a good way of not making mistakes. So for example, obviously the specific gravity for water is 1. Not uncommonly in atmospheric applications, instead of comparing the density or specific weight of a liquid to that of water, for atmospheric considerations, sometimes they'll use air. But that's not a common definition in the engineering application. This is the definition we would use. So, what I'd like to talk to you about next is elasticity. And again, in solid mechanics, you learn about elasticity by looking at solid objects. And basically all elasticity is the resistance of something to deformation. And there's a lot of different types of deformation you can have. But if you take this steel ruler and I just put a little stress on either end, you can see that it bends. And if I did it hard enough, I could actually get this past what we would call elastic response to more of a plastic response. What does that mean? An elastic response means I deflect it, and then when I release the pressure, it goes back to the original condition. It's an elastic process. If you bend it too far, it's just going to stay bent, right? You can even do this with a twist tie, same thing, because inside of a twist tie is usually a thin piece of metal. And then if this were concrete, same thing. You could actually be getting some elastic deformation, maybe some plastic deformation, but ultimately it would just break. So liquids don't tend to break. Again, I used to pass around all these toys, but I don't want to infect you all. So, in a liquid, if you push on one end, the deformation goes out the other. So in solids, when we talk about elasticity, we typically look at it along one dimension, along the length, the width, or the thickness. But in fluids, because the 3 dimensions are all connected because of the fluid continuum, we have to talk about elasticity on a bulk basis, a volumetric basis. But basically, similarly, if you had a fluid, if this little squeeze toy was a fluid, the fluid has elastic properties as well. We can compress it. So think of a basketball or a soccer ball. It's inflated to 10 psi, and you push on the outside. Usually you do that to see if it's filled or not. And when you release that pressure, it goes back to the original position. So that's the elastic response. And basically what you're doing is storing energy. That's what you're doing when you, for example, compress that. So, for the definition here of elasticity, what we first do is define actually what the opposite of that is. Before I go any further, I have 3 announcements. One is we are going to have lectures in grade 320, starting with the next class. Only 3 students have come forward. 4 students have come forward and said that they wanted to be in 320. So they'll be given an invitation, and if more students, we can fit up to 18 there. Basically, it'll be a big screen that you can look at. And hopefully I can yell loud enough that you can hear me over in Greg Hall from Chase. That's the first announcement. Second announcement is I will probably post a homework today or tomorrow. And whenever I post homeworks, the due date is right on the top of the homework. But more often than not, it's the very next class. Okay? And the third thing, because we've had so many difficulties in here, I'm giving everybody Monday off. So no class on Monday. Don't let the other faculty know about this. They'll think I'm going soft on you. All right? So I'll see you again Wednesday sometime. Those were the 3 announcements. So, for elasticity, how we usually define it is by defining actually its inverse. And what we'll say is we're going to define compressibility. And compressibility is going to be defined as the percent change in volume or density for a given pressure change. So if I put that verbal definition into a numerical definition or an algebraic definition, compressibility is going to be the percent change in volume. So let's look at an analogy. This is a thick-walled steel cylinder. And in that thick-walled steel cylinder, we're going to have a piston. And in the space contained in there, we're going to have some fluid. It can be a gas, can be a liquid. It's a fluid. And if we, for example, push down with some force on the piston, let's say that there's air in there, you know you're going to compress that air. And so with this as an analogy, we know we're going to have some initial volume, which we'll call V0.
So do you have to have your volume and then the TAs will all mute, will all mute because like it's just echoing.
How about now?
No.
Test that.
Who's been trying muting your volume?
My volume is off.
Yeah, try muting.
Is this unplugged?
How about now?
Is that better, everybody?
What's that? So, is that any better?
Test it. Check your
Okay. Is that any better? I guess we'll have to wait till the chat results come in. So we turn it up a little bit. And I'm not hearing any echo, so we're going to turn it up some more. Okay? Ooh, no echo. Very good. So So, we know we're gonna have an initial volume, and initially, we're going to have some,
There's still no sound.
so there was sound before, and now
So
there's no sound?
let me just unmute my volume.
Are you unmuted now?
Yeah, it's unmute now.
Okay, so, that's the delegate noise. How about now? That's not
Yes, they have
too bad. And you can hear me now? Feel like I'm in a phone commercial. Or the Twilight Zone. Okay. So we can have an initial force. And again, this is a cylinder. And inside the cylinder is a piston. And so we'll have an initial force, and if the underside of the piston has an area A, F0 over A, any force distributed equally over an area is a pressure. And so with F0, we have pressure P0 with initial volume V0. We can increase the force to F1. And by increasing the force to F1, that would obviously give us P1. And that would give us a change in pressure, whether we're talking at the differential scale or a finite scale, and that differential pressure would be the final minus the initial pressure. So with this definition in mind, we can say that the compressibility, the percent change in volume is equal to the change in volume over the initial volume, or at a differential scale, the differential change in volume over the original volume. And it's that change in volume, or that change, the percent change in volume, that's why we're dividing by the initial volume, to get the percent change in volume. That's a fraction for a given pressure change, either at the finite scale or at the differential scale. That's the definition of compressibility. But wait, there's more. Thought exercise. We have this piston. We started at F0. It's piston just sitting there. And then we push down on it. We go from V0 to V1. Did the volume increase or decrease? Chat people should answer this first, right? Increase or decrease? Should decrease, right? So that means in this context, this is a negative number, right? And if we left it this way, this property of a fluid, these are fluid properties, would be a negative number. And so to avoid that, we put a negative sign in front of it. So that's the definition of compressibility, and it just recognizes as you increase the pressure, the stress on the system, you're going to decrease the volume. Now, if you also look at that definition, it says that you can use the same definition for density. And in the case of making this definition on density, you will note that the negative sign is gone. When we compress this system, you have an initial density, rho 0. You have an initial mass in there. By compressing or pushing down on the piston, you have not changed the mass. same amount of masses within that cylinder, but you've decreased the volume. So the density went up. The final density is greater than the initial density. Hence, when you use the definition in terms of density, there is no negative sign. Okay? And just to go one step further, as we define this on a total volume, we could also define it in terms of specific volume. Change in specific volume over the initial specific volume for a given change in pressure. So that's pretty straightforward. And what you would see if we plotted stress on the vertical axis, and stress is calculated by the change in pressure, versus strain on the horizontal axis. At any point, we could plot stress versus strain. So remember, this axis, the farther and farther you go to the right, you're more and more negative. Okay? There's a negative sign here on this axis. So for example, 0 is here, and positive numbers are this way, negative numbers are that way. So with no change in pressure, you might have V0 and V1 being the same, right? And you would have some initial volume. We could look at this plot and we could identify how things should be plotted. As we increase this, typically what happens is we would have something that looks like this for liquids. And compared to solids, typically solids are going to look something like a straight line. And they'd be much steeper. So for example, the modulus of elasticity for steel is 100 times the bulk modulus of elasticity for water. So solids are much more resistant to deformation than liquids. Liquids deform easily. And so they're going to have a smaller bulk modulus. But what does this mean? What it means is, as you try to compress this cylinder more and more and more, as dP gets larger and larger, by going vertical, dV over V0 is not changing. You're not getting more deformation with more stress. Basically, when this curve goes almost vertical, what you have is what's called an incompressible fluid. And that's what most fluids do. Gases have much more deformation capabilities than liquids. And as you'll see when I do the example, very commonly in engineering applications, we assume that liquids are incompressible. Okay? So, this is just an example. This is what it typically looks like. If we then go to the definition of bulk modulus elasticity. That's known as capital A subscript V, and it's simply equal to 1 over the compressibility. So we would take the equations we've just put on the board. And just take the reciprocal of them. So for example, EV is equal to minus change in pressure over delta V over V, or it's equal to change in pressure over d rho over rho. And remember, delta V is the final condition minus the initial condition. The volume on the bottom is the initial condition. Same here, D rho is the final condition minus the initial condition. And this is the initial condition, the initial density. So it's consistent. So, again, many liquids have almost a vertical stress strain plot. Liquids are hard to compress. But that does not mean that the modulus of elasticity is not important with liquids. It's incredibly important. So, the end of the semester, you'll take either your fluids textbook or me and throw me into the reservoir. When you throw something into a pond, like a rock or me, what do you typically see at the surface afterwards? You see concentric rings moving away. Those rings and their velocity is a function of the bulk modulus of elasticity. So commonly, the people identify this velocity. It's called the wave celerity. So again, you throw a rock in the water here, you're looking down on a lake, and you see the concentric rings moving away, and they're moving at a velocity A or a velocity C. They're moving at the wave celerity. That velocity is the square root of EV over rho. So again, this is an important property. Just because we say some fluid is incompressible doesn't mean the compressibility isn't important. It is. In your houses, when you, those of you who said you had water hammer, when you have the water flowing and you shut the valve very quickly, you hear a banging in the pipes. The movement of that is at the wave celerity, the movement of that signal. And that's how we actually design pressure transmission systems for surges. That's what that is known. To put in a surge arrestor, you have to know those characteristics. The other one is, and I showed this in a slide the first day of classes, if you have an aquifer that's exposed in the mountains and then goes very low below the ground, and below the ground, it's sandwiched between two impermeable formations. Have anybody ever been to Yellowstone and you see the geysers? Those geysers come from the Madison limestone, which is thousands of feet underground. If you poke a hole, drill a hole down into the Madison limestone, the water will shoot sometimes hundreds of feet above the ground. So the water in that confined formation underground is under pressure. If you put in a well and you pump water from that confined formation, you do not dewater it. So where does the water come from? Bulk modulus of elasticity. You're getting the water from the expansion of water itself, from the change in density. And to another extent, the fact that when you relieve the pressure on that formation, that the voids actually start to collapse. So you've heard of Mexico City, Southern California. They pumped out so much water that they've had land subsidence on the order of 10 meters or more. It's the same principle. So again, some of these fluid properties operate in the background, and now and then they're just going to rear their ugly head and shock you. So I'd like to do a very simple calculation because most of my lectures I'll go through theory, and then I'll do an example, and then I'll throw a homework at you on something very similar. So So, simple question. What is the necessary increase in pressure to get water to reduce its volume by 1%? And again, think of what I just erased. So we've got our piston, and we have some volume in here, and we want to reduce that volume by 1%. And the question is, how much do I have to push down, or what's the change in pressure to create this condition? If you look at the definition of bulk modulus of elasticity, the denominator, delta V over V, that's the change, that's the 1%. It's a minus 1% because we're decreasing the volume. So that's a minus 1%. The question is asking for dP, what's the change in pressure? To solve that equation, you now have one other unknown, and that unknown is bulk modulus of elasticity. Do you know what that is? Can you find it? What's the fluid? If you're from Philadelphia, you would say water. Water. What's in your appendix? Fluid characteristics for water. Or you would go to the internet and find this for the temperature, which hasn't been specified. So, let me just let you know, from the back of your book, the bulk modulus of elasticity for water is 3.2 times 10 to the fifth. Help me out. I need dimensions on this. What are the dimensions of pressure? Force per length squared, so pounds per square inch. What are the dimensions of volume? Length cubed, cubic centimeters. What are the dimensions of change in volume? Cubic centimeters, length cubed. So what are the dimensions of the denominator? Delta V over V. Dimensions, right? So what's the dimensions of the right-hand side? The dimensions of pressure. Okay, so the dimensions are important. Whenever you write a number, write the dimensions. Unless you actually have a number that doesn't have dimensions. dV over V doesn't have dimensions. So what we have to do is rearrange that equation, bring dP over to the left, dV over to the right, and we can solve for this. So again, we're solving that equation, the definition of the bulk modulus of elasticity for change in pressure. And basically what that means is bringing minus delta V over V to the left-hand side, and you isolate dP. And so now what we have is, I'm sorry, I wrote that wrong. I should know, just like many dogs, I saw a lot of heads going like this, so that's equal to EV times dV over V0. Sorry. That's what I get from shooting from the hip and not looking at my notes. Great. So in this case, what we have is minus dV over V0 is 1%, which is 0.01. And the bulk modulus of elasticity is a supernatural spirit in here. So that would be equal to 3.2 times 10 to the third, or 3,200 PSI. So, question. Is that a high pressure or is that a low pressure? Do you have any feel for this? What do you typically inflate your bicycle tires to? Mountain bike, 20 to 40 PSI. Road bike, 80 to 120 PSI. What's the typical pressure you see in a water distribution system? Not uncommonly, 30 to 60 pounds per square inch, 30 to 60. So is that a large pressure for a water system? Absolutely. And that's one of the reasons we assume water to be incompressible. You need a huge change in pressure in order to get a significant change in the volume. However, as I mentioned with water hammer, when you have the water flowing and you shut the valve very quickly, or in a hydropower system where you have the pump all the way downstream of this enormous penstock, and all of a sudden the pump trips and stops the flow of water. When the water keeps rushing towards either the valve or the turbine, it can create pressures as high as 5,000 psi, enormous pressures. And I assume most of you have finished physics. Let's say I tie a rope to that wall and I send a wave towards that wall. What would happen to the wave when it comes back? It flips and it becomes negative. And that's what happens in piping systems. So that huge pressure surge, once it hits the valve, it may bounce back at, say, 4,000 psi. If it hits a bend in the pipe, it comes back as a reflected wave. It may be at minus 1,000 psi. Typically, the pipes can take the positive pressure, they can't take the negative. And so often what happens is they implode, and then when the pressure that is there afterwards, they then rust apart. And they're usually deadly when it happens. So these aren't trivial issues, and it has everything to do with bulk modulus elasticity. So, in the remaining 5 minutes, I want to, are there any questions from online? Besides, I can't hear. I want to introduce, and we'll be spending next class more on this, I want to introduce viscosity. And the simplest definition of viscosity is, it is the fluid property that offers resistance to motion. Okay? Elasticity is the resistance to stress, change in the form. Viscosity is relative motion between particles. Okay? And you'll hear, if you listen to some of the advertisements on radio or television, they talk about the viscosity of oil in your car and how when it gets really hot, the viscosity breaks down. So use our oil because it's the best. Viscosity has 2 fundamental building blocks. One building block is intermolecular cohesion. Like molecules like to be next to each other. That's intermolecular cohesion. The other building block for viscosity is intermolecular momentum exchange. And that is molecules bouncing into each other. And it's because of those 2 building blocks and the physical difference between a gas and a liquid why you get a very different response for viscosity, which we typically denote as the lowercase Greek letter mu, mu. So if you plot viscosity versus temperature for a liquid, it looks like this. If you plot viscosity versus temperature for a gas, the viscosity of the gas is much lower, but it actually increases with temperature. Why? In liquids, remember, there's 2 building blocks to viscosity. Intermolecular cohesion, and molecular momentum exchange. In a liquid, the particles are moving very slow. And because of that, there's not a lot of molecular momentum exchange. And so viscosity for liquids is dominated by cohesion. When you heat up a liquid, the molecules move farther apart. And so that intermolecular cohesion breaks down. And since that's what dominates viscosity in liquids decreases with temperature increase. For a gas, it's just the opposite. For a gas, the particles are far apart. So there's very little intermolecular cohesion. The particles are not only far apart, but they're moving very fast in a gas. And so there's a lot of intermolecular momentum exchange. By heating up the gas, the particles move faster. And so when they crash into each other, you get more viscosity, more resistance to movement. Okay? So again, there's a physical reason why these two operate differently, and it's not a huge issue. You just have to recognize, just like some of the other fluid properties, this is a temperature-dependent property. So, and this is where I'll end, just on the dimensions. So, first, what do we call it? Coefficient of viscosity, absolute viscosity, dynamic viscosity, or just viscosity. There is another type of viscosity we'll talk about, but this is really important. What we call something in an engineering sense may be colloquially called something completely different, and we're talking the same thing. So, for example, we were talking about inflation pressure for tires. We'll say, for example, 20 psi. Go to the gas station and they'll say, yeah, inflate it to 20 pounds. Right? So that's the colloquial way of saying pounds per square inch. Similarly, because there's two different types of viscosities, another variable we'll talk about, the top three are the more formal ways of describing what we call the stress-strain relationship for viscosity. Colloquially, in engineering, we call it viscosity, and we will not confuse it with the other viscosity. The other viscosity we're not going to call just viscosity. The other one, we'll call it kinematic viscosity. So that's what it is, and I see we're out of time, aren't we? Noon. We'll continue this Wednesday, right? Expect the homework posted today or tomorrow on Canvas with all the instructions on how to deliver it and who to deliver it to and how to deliver it. Thank you for your attention.